Welcome to the video presentation of Dungeons and Replicants, automated game balancing via deep player behavior modeling. This paper was published in the 2020 IEEE Conference on Games and is accessible via the link in the video description. In this work, we approach the interminable effort of online game balancing by incorporating gameplay models of actual individual players. Throughout the course of 6 months, we recorded atomic actions of 213 players of the MMORPG Ion, which were then used to train individual player replicants via deep player behavior modeling. Eventually, we utilized this representation of the player population for large-scale combat simulations against dynamic NPCs or each other, reveal significant balance differences within classes, and show how these could be regulated. Let's start with the problem. To consider a game balanced, the available option for character classes, factions, units or roles should mostly be viable, so that players of equal skill should have an equal chance at winning, regardless of their preferences. With modern multiplayer online games, available options, for example playable characters, have skyrocketed, which is again complicated with the number of traits, skills, items, etc. that can be modulated. While automated routines for the detection and reporting of critical errors and solvability already become more popular in the industry, balancing remains one of the most difficult and time-consuming phases of the game design process. Compared to straightforward fixable bugs or glitches, the trouble with balancing issues is that they do not only appear during the launch of a newly published game. Instead, balancing is an ongoing, repetitive task that is heavily influenced by the perceptions of the player community. In the industry, balancing is most often approached through long-term expert analysis, excessive human playtesting, and persistent debates with the community. Thus, even prominent titles of competitive online games that launched years ago still undergo persistent balance patches. Previous scientific work has tackled automated balancing before, in the most cases by simulating large amounts of gameplay sessions, assessing balance criteria, and iteratively tuning in-game parameters. However, to the best of our knowledge, all of these rely on either heuristic or performance-optimizing agents. While this might yield valuable insights for gameplay in general, it lacks the capability of representing the actual player population. On the one hand, the deployed artificial agents might be too simple to grasp human decision-making, and on the other hand, optimal agents that outperform human abilities would also skew the results with respect to the actual balancing among human players. Thus, we propose a solution to this by modeling the actual decision-making strategies of individual players directly from the population. As demonstrated in previous work, deep player behavior modeling is capable of learning strategies and action preferences of individual players and can then generate agents that are not distinguishable from the human originals in similar situations. But how does this work? To demonstrate the potential of Dpbm for automated balancing, we implemented and evaluated it on a private server on the MMORPG Ion. Similar to most classic MMORPGs, in-game battles consist mainly of the activation of different skill actions in different situations. According to previous expert interviews, this action selection is mainly influenced by the player's preferred skill rotation, that is, the personal sequence in which they would like to execute these, and responsive decisions, in that they have to react to low HP with heals, debuffs with cleanses, distances with movement skills, or the like. Thus, the Dpbm architecture looks as following. A huge input vector is constructed that contains current game state information about the player, his target, and the skill history. This is then mapped to the executed skill in this situation via machine learning, in this case multilayer perceptrons. Given that enough data is present, this model can then generate skill preference distributions in similar situations that have already been observed. Eventually, these preference distributions are filtered by heuristic constraints, and the most probable action is calculated by a weighted selection. To accumulate sufficient amounts of gameplay data that this approach builds on, we utilized such state action records from a previous study where players encountered challenging 1 versus 1 encounters on a daily basis. Over the course of 6 months, this produced enough information to populate replicants for 213 players. Even if this requirement for human data renders it not really viable for newly launched games, keep in mind that balancing is a long-term effort that this approach seeks to optimize. With a set of over 200 representative agents trained, we aimed to detect balance discrepancies between the classes of Ion with respect to one-on-one player versus environment situation, as well as in player versus player constellations, to answer the following research questions. Can imbalances between in-game classes be detected through generative player modeling with respect to PvE and PvP? And can generative player modeling elevate automated game testing to turn design specifications into optimized parameter constellations? To go deeper into detail, we compared 10 different classes that focus on different styles of playing. To quickly sum them up, melee classes mainly deal close combat damage, in contrast to distanced magic classes or ranges. Heal classes deal less damage but offer additional support, while chanters excel at the latter. Even if many in-game situations involve multiplayer constellations, all classes are able to perform on their own in principle. Now, to benchmark the different classes with respect to their PvE capabilities, each of the 213 player replicas encountered 100 heuristic PvE opponents with iteratively increasing difficulty. To keep the simulation visualizable, this difficulty was only manipulated through two dimensions: offensive capabilities, attack, and defensive capabilities, maximal health points. These increased by 25% per iteration, from a trivial encounter up to a barely defeatable enemy. This certainly leads to a distribution of enemies that could be defeated by the player replica versus those that the individual agent could not overcome. In other words, for every individual player replica, we identified the limits of its capabilities. To quantify this information, all of the respective outcomes were not only recorded binarily, but using a proficiency metric. This proficiency metric takes into account the binary value of having won against the opponent, the normalized temporal duration of the fight, the agent's remaining HP percentage, and the opponent's remaining HP percentage. All variables lie between 0 and 1 and are normalized over the sum of observations, resulting in the final proficiency phi that ranges from worst case 0 to optimal 1 performance. For the average player, this phi resulted in 0.68, with a clearly visible decline in proficiency as the difficulty increases, whereas the capability limits of the best and worst player are significantly shifted. So what do we get if we compare the resulting phis from all player replicas? Using a one-way ANOVA, we found a significant difference across classes, which were further investigated with pairwise t-tests. As a result, the Spirit Master, Gunner and Bard classes scored significantly higher than most other classes, while Chanters and Templars were almost consistently outperformed. Additionally, random or generalized models of the classes, that took into account data from not only individual players but the whole set in a class, scored significantly lower than individual models, as indicated by the circle and diamond marks in this plot. Although this approach primarily focuses on informing game development about balance discrepancies, some regulation techniques can follow immediately, assuming that all classes should follow a similar proficiency distribution. Within this regulation, we reversed the process and approximated viable offensive and defensive values for enemy encounters by calculating the mean proficiency of all classes and computing the mean squared error of all measured proficiency values for each player and every class. From this, we reveal the approximate parameter values to tune by calculating the center of mass of these errors per class. Eventually, when comparing classes for the regulated enemy parameter values, no significant differences in proficiency remain. In contrast to the former PvE evaluation, player replicas competed against each other in the following PvP benchmark. The proficiency outcomes of these matches were pooled and averaged to measure systematic dominance or inferiority relationships between classes. As a result, classes within the same archetype had few to no significant proficiency differences, but distinct superiority relationships emerge when different archetypes are matched up. Rangers, for example, scored significantly lower against melee classes, yet they consistently outperformed the magic classes. The magic classes were equally and consistently able to dominate melee classes, effectively representing a rock-paper-scissors-like interaction scheme. The heal classes also outperformed melee, yet succumbed to both rangers as well as to the magic classes. So, we revealed significant differences in proficiency between player replicas of different classes. This might indicate imbalances of these classes, yet it should be interpreted with respect to the underlying design intentions. For instance, the relatively low proficiency scores of the Chanters and Templars likely stem from the reliance on other players, either to support or to receive support from, respectively. Still, under the assumption that primarily damage-dealing classes should be equally viable, certain discrepancies emerge that point to certain magical classes outperforming physical damage dealers significantly. With the proposed regulation techniques, this could be sufficiently balanced within single-player scenarios. When interpreting results of the PvP benchmark, it is worth noting that balanced viability does not necessarily have to result in each class having equal chances against all others. Depending on the underlying design agenda, a similarly balanced constellation is a rock-paper-scissors-like interaction scheme between classes, which this evaluation was able to demonstrate approximately. All of the evaluated and regulated scenarios in this paper were limited to solo play. To consider interaction between multiple players and the effects of regulating onto the global balancing, iterative procedures of attunement and resimulation would be expedient that automatically identified the largest proficiency mismatches, calibrate and resimulate. To wrap things up, significant imbalances between in-game classes can be detected by incorporating decision-making from actual players through deep player behavior modeling. Instead of generalized or performance-optimized agents, individual models have shown to closely represent the player population. Using the insights from these DPBM-driven simulations, developers can implement their design specifications manually or via the proposed regulation methods. This evaluation is based on preceding work on deep player behavior modeling. Apart from the application area of balancing, similar successes and accurate player representations could already be examined for substituting disconnected players in online matches or elevating long-term dynamic difficulty adjustment. Check the featured articles for related work on DPBM. Thank you very much for your attention. If you have any questions, remarks, ideas or collaboration proposals, don't hesitate to contact me using the provided email address.